The past two talks we heard about elliptic curve over complex numbers and a bit about modular groups, modular forms, and all of these things. And I mean, you could go on and on and on about this, but I think we've had enough of an introduction now to actually talk a bit about what I really want to talk about, which is complex multiplication. So let me write this down. Complex. And let's do a quick recall of what we saw. This theorem where we took an elliptic curve E over the complex numbers. And bigger than 1. And then we saw that we can look at this portion group Bm, yeah, which we define to be all the points on E, basically such that m times E point 0, right? And so we have this map which goes from E to E, and it takes a point P plus P plus P plus P, and so on and so forth, m times. So let's do a quick drawing of how this could look like, right? So for us, an elliptic curve is a lattice like this, right? With these periods omega 1, omega 2. And now if I take, say, the distortion group M, this I would get this by just dividing these two lines, omega 1 and omega 2, these two vectors, into M equal parts. So just dividing it up, so on and so forth. And then I look at all the intersection points here, all of these directions. Yeah. And all of these points, they will be my torsion group. And why does this work? Let's look at a very easy example. Let's just look at the 1 and I lattice. And let's maybe look at the 2 torsion. So what's the 2 torsion? So we have our origin O here. Now we divide this into 2 parts. So I have 1 point here, I have 1 point here, and I have 1 point here, right? So if I actually look at this vector, the vector that goes in this direction, let's call this say V. So if I actually do V plus V, which brings me up here, and then if I mod out by the lattice, and this sends me back to 0. Okay, so V certainly is in proportion. And then maybe let's look at this vector. Let's call this W, right? So if I look at W plus W, and again this is 0, right? Let's look at W here. Yeah, and then I have a third one, which is the linear combination of V plus W, right? So I can have a third vector. Let's call this Z maybe. That would be W, and then again Z plus Z, mod lambda is equal to 0. At this point here, mod lambda just collapses back down to 0. So this would be right, and then you can just do this for any integer that you like. Okay, so this gives me the torsion group. So what we see is if I take an elliptic curve over the complex numbers, then any M torsion exists. Yeah, and this is actually a bit different to elliptic curves defined over other fields, because for those, maybe not all the M torsion might exist. Or maybe all the M torsions only exist over some closure. But over C, you just divide your lattice into M points, and then you always get these torsion groups. So that's quite nice. And we also saw that the structure of this M torsion, that this is just 2 copies of Z mod M, right? Just 2 copies of these groups here. And if M is a prime, then you just have 2 copies of cyclic groups, for example. And you can kind of see this, right? Because one direction here gives you 1 copy, and the other direction here gives you another copy, and then everything that's in the diagonal is just when this product here mixes. Okay, so this is something we saw. Now we also had a second theorem. Again, this is just recalling what we saw before. We had we took an elliptic curve over the complex numbers again, and then we said that to this elliptic curve, say there is this lattice that corresponds with, which I'm going to normalize as Z plus Z, right? We saw we can always normalize it like this. This should be the lattice associated to E. Then we saw that the endomorphism ring of E is either. So first of all, okay, so in this case the endomorphism ring is very simple. Or, and there was a second possibility, actually, that N of E, and this was isomorphic to an order in Q tall, right? And Q tall is an imaginary quadratic extension of Q. Okay. And in the first case, we called the elliptic curve ordinary, because this is just what happens in the ordinary case, and for most of the elliptic curves, this is true. And in the second case, we called the elliptic curve, in the second case, the elliptic curve is a bit special. So what we said is in the second curve is that E has complex multiplication. It has Cm. So I'm going to abbreviate this by. And this just means that the multiplication by M maps are not the only maps, right? Because we said for every M, there's a multiplication by M map. So the endomorphism ring in the first case certainly has contains all this multiplication by M maps, but sometimes there are just more maps. And as we're going to see, this has something to do with certain symmetries of the underlying lattice, right? If you think about the example I showed you earlier, the 1I lattice, then there's actually also this action by I. There's also an action by I in the lattice, which induces a symmetry. So this curve certainly also has complex multiplication. The endomorphism ring is going to be a bit larger. And what you're going to find actually is that for this example earlier, this curve where the lattice is 1 and I, that the endomorphism ring is actually going to be Zi, right? And this certainly is an order in Qi, which is the square root of -1. And this is a quadratic imaginary extension of Q. So this is true, right? This is one example. And this curve has a complex multiplication. So today what we would like to look at are the first gentle steps into the theory of complex multiplication. I mean, it's very, very big, but we'll just see a bit of the introductionary theory. Okay. So let me quickly recall a definition, because I just said the endomorphism ring is an order in Q. So let's quickly recall what is an order. So consider a number field K, and the number field is, for me, is just some extension of Q, right? Now, an order, say R, A, is simply a subring K, yeah, which is finitely generated as a Z module. Okay, such that if I tensor over Q, then I just recover my whole field K. So if I consider R and the field extend. So what you can think of R is some sort of ring of integers, right? So the ring of integers in a number field is certainly going to be in order, but you also have different orders. Okay, but the ring of integers could be an example, right? And then if I take the ring of integers and I field extend it over Q, I just recover my number field again. So this can be one example. And I should also make a remark here that this notion of order is a bit more general, okay? So you also have orders in Q algebras in general. And it doesn't even have to be a number field. It could also be a quaternion algebra. Okay, etc. In the case of quaternion algebras, we will only actually consider whenever we might talk about elliptic curves over finite fields. Let me just quickly say something about that. So the endomorphism ring for an elliptic curve defined over a finite field is always bigger than SAD because you always have an element called the Frobenius, which acts non-trivially. So the endomorphism ring always is at least an order in an imaginary quadratic extension, but sometimes it's even bigger than that. Sometimes it's actually an order in the quaternion algebra. But this will not happen for when we consider elliptic curves over C. So the only two possibilities are the ones we said earlier. But this is just a side note. Okay, now from here on out, let's assume that for simplicity, because this case is actually easier to analyze, that let's assume that we have Cm by Rk actually, where Rk is the ring of integers of an imaginary product number field. The ring of integers of some imaginary quadratic number field. Okay. Okay. And this is nice. So Rk is actually a maximal order. Okay. So we said the ring of integers is certainly an order, and this is actually an order that does not sit in any bigger order. So the ring of integers is a maximal order. Okay, so but there could be other maximal orders, but for simplicity we're going to consider this case. Now let's do another recall. We saw that for every elliptic curve P defined over the complex numbers, there exists this lattice in the complex numbers, right? And then we have this mapping. So we have a map from C mod lambda, which actually is an isomorphism to this elliptic curve, which sends Z to, and then we looked at these Weierstrass P functions the other time, depend on the input parameter Z, and also depends on the underlying lattice. Right, and X gets sent to P and Y gets sent to first derivative. And the corresponding elliptic curve, right, which we call E lambda here, maybe is given by y square equals minus g2 of lambda x minus g3. Right, and g2 and g3 were these Eisenstein series that also depend on my lattice. Okay, so that's basically what we're going to use here to analyze the Cm case by Rk, this duality. Now there's a proposition. So consider curve over C with Cm multiplication by some ring lying in C, right? Now, for example, So maybe you have this extra map I that acts in the curve. Now there is a unique morphism, okay, from R, from this ring, into the endomorphism ring, right? Because in general, this ring R, it might be isomorphic to the endomorphism ring in more than one way, right? There could be more than one embedding for it. So we should fix actually one. And now this proposition tells you that you can always fix a unique embedding for this endomorphism ring. And now how does this work? So this works for any invariant differential. I mean, we haven't really talked about the theory of invariant differentials much. That's fine. There exists this object that's attached to a curve, which we call an invariant differential. And so the idea is that I can choose my isomorphism in a way. If I push forward, if I push forward this, no, if I pull back this omega, then it's, So if I consider omega, the invariant differential on my elliptic curve, then if I pull it back through this isomorphism, then this is just multiplying the invariant differential by this complex number. Okay, and this is the way we're going to fix it. And this works for all alpha and R. Okay, so from now on, really what we should think about is elliptic curve E together with this embedding. Yeah, this fixes embedding R into the endomorphism. Okay, that's actually quite important. Okay, and yeah, from now on, when we talk about that, when we just say an elliptic curve, we really think of the elliptic curve together with this specific choice. Now, how do you actually see that this exists? So recall that the endomorphism ring of the E lambda, right? And this should be isomorphic to R. Now R, if we actually look at the right side of this equation, so you look at all the alphas in C, right? Such that alpha lambda lies in lambda, right? And this is what we call isogeny. Yeah. If lambda 1 and lambda 2 were two different lattices, but now I actually want to look at all the alphas that send the lattice to a sublattice, right? So isogeny actually, this in this case is like a self-isogeny, right? And that's really what we said was an endomorphism. Okay, and this whole set, right? Now, so really what you do is you look at C mod lambda, and you look at this map phi alpha, which just sends Z onto alpha times Z, C mod lambda, because this is a sublattice. And then you have this function f, which we saw earlier, right? This function f was our isomorphism from C mod lambda into the elliptic curve. Okay. Now, what happens here is you consider this alpha, and you send it to this endomorphism alpha in bracket. Okay. And now you want to make this diagram commuting. Okay, so basically for every alpha and R, there exists a map alpha which goes from E lambda, right? That diagram commutes. And that's actually not too hard to show. And then basically, once you have this alpha, you just check how it acts on differentials, and then you'll find this property that you need in the proposition. Okay. Now let's assume that we have this embedding. Okay. And this embedding is important because it plays nicely with isogenies between curves as well. So there's a quick corollary. So what you look at is you consider two of these normalized curves, is what you're going to call it, curves together with an embedding. You consider E1 and E2. So two normalized curves. Okay, so normalized we're going to call a curve if it comes together with the embedding we chose earlier. Then for say isogeny of phi from E1 to it holds that if I embed first and send the point through the isogeny, this is actually the same as on the other curve and sending the point through the isogeny first. For all essentially, if you choose this embedding, then it commutes with the action of isogeny, and that's quite nice. Okay. Now, remember when we considered the set of all elliptic curves up to isomorphism. Here we would like to make a bit of a restriction of this set, right? Remember when we considered the set of all elliptic curves over the complex numbers. So now what we're going to do is we're going to restrict this to all elliptic curves to have complex multiplication by some range. Okay. So we will define L of R, and we say this is the set of all elliptic curves E over C and the morphism range. Okay. I remember we also had to mod out the isomorphism earlier, so we shall do the same thing here because we really want to consider isomorphism classes because all the curves in the same isomorphism class they essentially are the same anyways. So let's mod out isomorphism over C, right? And then by what we saw in the past few minutes, this should be the same as all lattices on lambda with the morphism ring attached to elliptic curve is not the same as R. And then we said last time that isomorphism over C for an elliptic curve is equivalent to homotheity for the attached lattice. Okay, so in the next maybe half an hour or so, what we're going to consider is this set Li. Okay, so a good question maybe is how do you construct a curve that has complex multiplication by a certain ring? So we're going to start from an imaginary quadratic field K. Okay. And we're going to consider the ring of integers Rk and K. Now, how to construct such that the morphism ring of this curve Rk. And actually, turns out there's a very natural way to do this. So what you do is you take a fractional ideal of K. So say we take some fractional ideal A of K, C, then the theory of fractional ideals actually tells you that A is a lattice. Let's see. And what this means that actually A is a set module, okay, and of rank 2. So you really want to have two generators that are independently over the reals. So because I mean we chose K to be an imaginary quadratic field, right? So in this case, any fractional ideal of K is rank 2 set module. So you can really consider it as a lattice. And now I can look at this thing here. I can actually consider the elliptic curve that's generated by A considered as a lattice. And it turns out that the endomorphism ring of this thing will actually be RK. So let's look at this. So n of P, where the lattice is this fractional ideal A, this is isomorphic, right? So all the alphas in C, yeah, such that A acting on alpha is contained in A, right? That's how we defined it earlier. But now this set is simply all the alpha in K, right? Such that A is contained in A because it's a fractional ideal. Well, and for all means and purposes for us, okay, because A is a fractional. Nice. So now we know how to construct elliptic curves that have a certain RKS and morphism. But now we also know that all homophadic lattices, they give isomorphic elliptic curves. The homophadic lattices isomorphic elliptic curves. Okay. But two fractional ideals might still represent the same lattice, right? So we need to do what we said and mod out by homophily. Okay. So in our case, what we're going to mod out is all the principal ideals, right? So we're going to consider the set of non-zero fractional ideals. Okay. And then homophily in this case is actually being the same after principal ideal. So we should mod out by all the non-zero principal ideals. Right, but we know what this group is that we just looked at here. This is just the class group of our quadratic imaginary number field, right? So actually, really, what this is just the class group of K, right? So this is really the ideal class group. Okay, that's pretty cool, because now what we get is we get the map from the ideal class group to the set of elliptic curves at complex multiplication by RK. And the way it works is we send an ideal class, then present it to the elliptic curve with respect to this lattice. Okay, this thing is the ideal. And if you have never heard about fractional ideals before and whatnot, I mean, you can read it up pretty quickly. It's not a super complicated concept. So why it's called a fractional ideal is basically um, you consider an object which, if you somehow clear out the denominators by elements in your ring of integers, becomes an ideal in the ring of integers. So in a sense, what you do is you just consider fractions. So you consider an ideal, and then you divide by a few elements. And that's basically what a fractional ideal is. So it's not a hard concept or anything. Anyhow, so now we have this map here, right, from the class group into the set of all elliptic curves with complex multiplication by RK. But turns out actually that this map actually gives us sort of a group action, right? Because CL, this here is a group, and from what we get from this map is actually a group action of the class group on the set of elliptic curves that have complex multiplication by RK. Now let's formalize this a bit. So there's a proposition. First of all, let lambda be a lattice. A with lambda the corresponding elliptic curve by RK. Now we consider two ideals, A and AB, non-zero fractional ideals. And then the following. So first of all, as we said, A lambda is like this. And what do I mean by A lambda? For this, I just consider all linear combinations. Basically, alpha 1, lambda 1, plus, and so on and so forth. Alpha r, lambda r, yeah, for I in the ideal A, lambda I a vector. This is sort of it. Just take all the possible linear combinations. I mean, what this gives me is just an action of the fractional ideal on the lattice. And second, now I just said this is a lattice, so I can also consider the elliptic curve that's attached to it. And so I can consider E a lambda. And actually, it turns out this satisfies, again, the endomorphism ring of E a lambda equal RK. Okay, so that's cool. So if I act with A on this lattice, I don't change the endomorphism ring. But that's why I said it's a group action, and it just kind of keeps me in the same orbit. And also turns out that E a lambda is isomorphic to E B lambda if and only if A and B are in the same ideal class. Okay? Yeah, and as I said, from this we get an action. The class group on the set of elliptic curves have complex multiplication by RK. And now how do I define the action? Well, let's say this ideal class acts on the curve E lambda by just considering the curve A minus 1 lambda. And that's why I actually want to have non-zero fractional ideals, right? I want to actually be able to invert these fractional ideals. And the reason why we invert here is just for convenience, like, because it keeps certain ordering nicer, and it makes composition of these actions nicer. And now let me interject here just a remark for cryptography. actually important. There's a crypto system called Seaside, which exactly considers this group action sort of as something called a hard homogeneous state. So if you have a group and you consider exponentiation on a discrete group, then there's something called the discrete logarithm problem. But you always have the group structure. Now the idea was, could I maybe take away the group structure? And it turns out that if I consider this group action, then you can still have something like a Diffie-Hellman problem on it, but you take away the group structure by having the set on the right side and on not a group anymore. But that's just a side remark. Now we said we have this group action, so it turns out that this group action that's L and RK. This is actually simply transitive. This means that from every point I can reach any other element. And then by the orbit stabilizer theorem, I'm able to count how many elements I have in my set L. And this is just the size of the class. Okay, that's nice. So if I actually know what the class numbers of RK, then I actually also know how many elliptic curves I have with complex multiplication. Okay. Now, let's consider some examples maybe. Let's start with the one we already saw, lattice generated by 1 and I. So let's look at lambda, which is just that I. Right, and we saw this is just a ring of integers. Okay. I guess people call them the Gaussian integers. Then morphism ring of the attached to the curve lambda simply the propositions we saw earlier. And now if you actually think of this lattice and how many automorphisms this lattice has. So this lattice is certainly invariant under the action of multiplication by 1 and minus 1, right? You flip it, you mirror it along the y-axis, but you can also mirror it along the x-axis because in the sense the lattice is just rectangle squares of equal edge length, right? So the automorphism group of lambda, therefore also the automorphism group of d lambda, right? This is the mirroring along the y-axis, and also plus minus I. This is the mirroring along the x-axis. And now actually, in the original Silverman book, by elliptic curves, this is found in chapter 3, there's theorem 10.1, where he classifies elliptic curves up to automorphism groups. This actually implies that the J invariant lambda has to be 1728. Okay, this is the only elliptic curve that has an automorphism group of size 4. And now we can try finding a model actually. So let's look at I lambda. We said that lambda is invariant under the multiplication by I, right? That's automorphism. So this is just lambda. Therefore, G3 lambda, right? This should be the same as G3 of I lambda. Now, if we remember that G3 was actually a modular form of weight 6, right? This has to be I to the 6 G3 of lambda. This is just for the modular form x. I to the 6 is just minus 1, so this would be minus G3 of lambda. Okay, so G3 of lambda is minus G3 of lambda, therefore G3 0. Cool. So from this we find the model lambda, which is just y squared equals 4x cubed minus e2 lambda x. And turns out that because the chain variance is actually a rational number, that there should be a model defined over the rationale. And actually, you can find this elliptic curve here, which is isomorphic to this one, which is given by y squared equals x cubed plus x. Okay, and this is a rational number. But I mean, nota bene here. This is an irrational number. This is definitely not irrational. Okay, not irrational. Here's an isomorphism that makes it. Okay, this is one example. Now let's have a look at another one. So consider the root of unity. So which is equal to 2. So we're looking at the cube root of unity. So like this well. Now rho of lambda is by the same idea as above. So now looking at T2, which is a modular form of weight 4, you find actually the T2 should be 0. And then I find the model A lambda y squared is x cubed. Cubed lambda. Again, I can look at the automorphism group and find this 1 rho plus square. And this is an automorphism group of order 6. And again, there's a unique elliptic curve. And this is the unique elliptic curve with chain variance 0. So we also find here that here is just 0. And again, because this is the rational number, we should have a model that's kind of the rationals. Turns out there is one given by y squared. Okay. So these are two nice rational elliptic curves to find out the rationals with rational chain variance. And these are probably two of the most famous chain variants, say 0 and 178. So for some reason, this number 178 appears all over the place. When I say for some reason, this is a bit of an understatement. I mean, there are many reasons. Now, let's see, we have 10 more minutes. So I think I will be able to say a bit more. So remember when we considered we can actually define something a bit more general. We can define EF fractional ideal A, which we're going to call simply the A portion. So these are all the points in the curve such that if I access alpha T, transfer to the identity for all. Okay, and this is what I'm going to call the A portion. And remember, this is possible because for some elliptic curves, alpha uh, alpha need not only be the integers, right? So for example, for this example that you see up here, there's also a map rho, right? So we also have something rho for the E lambda up here. Or maybe if I want to be a bit simple, I can also consider an RK, which just but there is a more general sort of structure, of course. Now, remember when we said that the kernel of an isotropy should be a cyclic group for, well, not a cyclic group, but the kernel of an isotropy is given by sometimes by this multiplication by maps. And again, we can generalize this a bit. If you take some integral ideal of RK, in that area, the integral ideal RK, lambda is certainly contained in h to the minus 1 lambda. what you get actually is a map like this, which sends said, but now in this super lattice. Okay? It turns out that this homomorphism here proves actually induces ionization. And we start, right? Because this is just how we define this. We define this as p minus 1. Okay. So we should be able to recover the kernel of this assumption. Right? For this actually we have to follow in focus. So let me use an elliptic curve with complex multiplication by m. A as a dot, an integral ideal of rk. Then we have the following, namely that A is the kernel of this map. This is isogeny from E to A star E. Okay. We have that actually A, this is a free rank 1 RK mod A module. This is free rank 1 I actually was planning to show the proof of one, but I'm just going to forego this now because I haven't done that. But what I'm trying to say is that we can find more general assumptions, but the kernels of them are still defined. Same as before. Okay. So here's a corollary, which I'm not going to write down, just really, really quick instead of writing out everything. So the degree of this method from P to progeny here, yeah, this is just the norm of this ideal. Okay, it's the ideal norm of that. And then for all alpha rk, and we have that the degree of this induced method again, it's just the norm element out. So this gives me correspondence between the analytic data here and the algebraic data of the degree of the map. Because this map really is given by the polynomials, the fractions of polynomials over cxy. Right? So this degree really coincides with the analytic data on the other side. When if I just consider alpha as an element in my order. Okay, so this is important, but it's good, right? Because this coincides with the degree on the right. Now, the last part that I wanted to talk about today are a few rationality questions. And I'm just going to start introducing them, but I don't know how far I'm going to get actually because they're only 5 minutes. So, maybe instead of talking about it, I should just talk about the idea of these rationality questions. So the idea is that by considering the chain variant of the first complex multiplication, also by considering the torsion structure, yeah. If I look at the coordinates in here, then these numbers, using these numbers, I will be able to construct a Boolean field. Okay. So the idea is if I consider K, the imaginary quadratic field that I started with, and I join this number, yeah, then I can build a field extension from this by considering this torsion structure here. So I can also consider, and I can also join all the coordinates of my torsion. It turns out that this is actually an abelian extension A of this is highly non-trivial, and maybe I should call it that. Maybe if you take a lot of this thing, what I'm trying to say. This is non-trivial, but this is quite interesting because from classical theory and the introduction to that, and maybe Kumar theory, but we actually know a similar case where this happens, right? So, and basically a cyclotomic extension. So what you do is you take some, I shouldn't call this mu, right? I should I'll call it eta because it's easier for me to write. So what I'm going to take is eta and c, which is a primitive n through the primitive. Basically a solution of this equation over c, right? And then I take an element in my Galois group of q extended by eta over q, okay? Then actually, if I act by sigma on eta, this is another primitive to the primitive. And I'm just going to denote the group of primitive groups by mu n. Eta mu is another element now in mu n. And because mu n is cyclic here, this means that I can actually write eta sigma as the original eta here times some exponent which corresponds to this Galois element sigma, right? And this now gives me a Galois action of the Galois group of this extension over Q on, on this automorphism group of mu n, and this is just okay. And turns out that this thing here, if you work it out, this is an injective homomorphism. And also it's also true that Q eta over Q is an extension. Okay. So that's the easy part. And now I have a corresponding proposition in a sense for what I said earlier, elliptic curves if I started joining these elements. So if you combine everything that we saw, you get this proposition, namely K over Q is some quadratic imaginary and field. Okay. Then there exists a homomorphism F with Galois group theta over okay. That sigma sigma all Oh, again, this is important. F is actually independent. This works for all elliptic curves in this set. And this would be the analog for elliptic curves that have complex multiplication by arc. You also get some Galois action on this class group, which um, translates the action by the Galois group into an isotomy acting on the set of elliptic curves with complex multiplication by arc. Right? Because from earlier we get this class group that this class group actually is. And now the interesting part is that this F really is independent. Okay, now to figure out why this actually happens and whether you can generalize this a bit, and it's true you can generalize this and then there is much more theory behind that. We need to talk a bit about class field theory first, and we might do that in the future. But for now, I will just stop here. Yeah, thank you.